The next interference effect we want to discuss is a standing wave. Standing waves can arise with transverse waves, such as those on a guitar string, and also with longitudinal waves, such as sound waves in a flute. In any case, the principle of linear superposition provides an explanation of the effect, just as it does for diffraction and beats. To see how standing waves are produced, let's consider transverse waves propagating on a string. One end of the string is held fixed, say attached to the wall, and the other end is moved up and down, causing wave pulses to propagate down the string. Standing waves arise because identical waves travel on the string in opposite directions, and combine in accord with the principle of linear superposition. A standing wave is said to be standing because it does not travel in one direction or the other, as do the individual waves that produce it. The figure shows why there are waves traveling in both directions on the string. When the half cycle reaches the wall, it causes the string to pull upward on the wall. Consistent with Newton's action-reaction law, the wall pulls downward on the string, and a downward pointing half cycle is sent back toward the left. Thus, the wave reflects from the wall. Upon arriving back at the point of origin, the wave reflects again, this time from the hand vibrating the string. For small vibration amplitudes, the hand is essentially fixed and behaves as the wall does in causing reflections. Repeated reflections at both ends of the string create a multitude of wave cycles traveling in both directions. If the timing, i.e., the period of the new waves, matches the return time for the reflected waves, then they reinforce each other and a standing wave is formed. The period of the new waves being created is just 1 over their frequency, and the time it takes a wave to travel the length of the string and back will be equal to 2L over V, where L is the length of the string and V is the wave speed. These two times must be equal for a standing wave to be produced. Repeated reinforcement between newly created and reflected cycles causes a large amplitude standing wave to develop on the string, even when the hand itself vibrates with only a small amplitude. Thus, the motion of the string is a resonance effect, analogous to that discussed in section 10.6 for an object attached to a spring. The frequency F1 at which resonance occurs is sometimes called a natural frequency of the string, similar to the frequency at which an object oscillates on a spring. There is, however, a difference between the resonance of the string and the resonance of a spring system. An object on a spring has only a single natural frequency, whereas the string has a series of natural frequencies. The series arises because a reflected wave cycle need not return to its point of origin in time to reinforce every new created cycle. Reinforcement can occur, for instance, on every other new cycle, as it does if the string is vibrated at twice the frequency F1, or F2 equals 2F1. Likewise, if the vibration frequency is F3 equals 3F1, reinforcement occurs on every third new cycle. Similar arguments apply for any frequency F sub n equals n times F sub 1, where n is an integer. As a result, the series of natural frequencies that lead to standing waves on a string fixed at both ends is given by the following. The following figure shows some of the essential features of transverse standing waves. Notice that the patterns include special places called nodes and antinodes. The nodes are places that do not vibrate at all, and the antinodes are places where maximum vibration occurs. To the right of each photograph is a drawing that helps us to visualize the motion of the string as it vibrates in a standing wave pattern. These drawings freeze the shape of the string at various times and emphasize the maximum vibration that occurs in an antinode with the aid of a red dot attached to the string. Each standing wave pattern is produced at a unique frequency of vibration. These frequencies form a series with the smallest frequency f sub 1 corresponding to the one loop pattern, and the larger frequencies are integer multiples of f1 as the figure indicates. Thus, if f sub 1 is 10 Hz, the frequency needed to establish the two loop pattern is 2f1 or 20 Hz, whereas the frequency needed to create the three loop pattern is 3f1 or 30 Hz, and so on. The frequencies in this series, f1, 2f1, 3f1, etc., are called harmonics. The lowest frequency f1 is called the first harmonic, and the higher frequencies are designated as the second harmonic, 2f1, the third harmonic, 3f1, and so forth. The harmonic number, first, second, third, etc., corresponds to the number of loops in the standing wave pattern. The frequencies in this series are also referred to as the fundamental frequency, the first overtone, the second overtone, and so on. Thus, frequencies above the fundamental are overtones. Since the two fixed ends of the string are nodes, the length L of the string must contain an integer number n of half wavelengths. Using this result for the wavelength in the relation f sub n times lambda sub n equals v, we can show that f sub n times the group 2L over n is equal to v. This can be rearranged to give our previous result.